I'm going to, again, as usual, give you some of the previous slides, which will be reviewing the classification loss, the cross entropy that we talked about last time, regularization, L1, L2, RNN. And then today, hopefully, we'll try to talk about LSTM, and then autoencoders and variational autoencoders, and hopefully start with the topic of generative adversarial networks, GANs. Okay. Right. So if you look at the last slides, this is what we had. We've already gone over it. So I'm just quickly going to skip over all these slides. We talked about categorical cross entropy. When is categorical cross entropy used? In classification. Basically, in classification where either binary or cross, binary or cross entropy categorization, but it's primarily used when you have classification as opposed to regression. Okay, and you've got this fancy equation of a log. We'll come across this again today. So just we won't go through it in as much detail, but just to keep that in mind. Okay, that losses sometimes do have logs in them. We spoke about regularization. We talked about dropout, L1, L2. In L1, L2, we had a loss. We had a primary term, and then we also had a regularization term, right? And we also had the parameter alpha. And so the alpha parameter was used to be able to control how much of the regularization you want. So we'll also be seeing slight variations of this as we go through today's lecture. Okay. So this was, and then we had recurrent neural networks. We had different examples of these. So we've already spoken about all of this, quickly going over all of this. And then we started talking about the concept of what are the problems with RNN. Okay, so the biggest problem that we said was the fact that when you have a long passage, let's say if you have a long conversation going on, and if you want to remember something after a while. So this was the example I spoke about that is often used. I traveled to France, blah, blah, blah. And then I eventually learned a certain language. So it has to remember that after many, many, perhaps sentences, okay? And the problem with RNNs was that because of, all the gradient descent algorithms, it would eventually forget what it was originally talking about, okay? So it is hard to have long-term memory. And so we didn't really talk about the solution to this, but we talked about how we're going to change the model so that when I do introduce LSTMs, it doesn't come out as a complete surprise. Looked at how RNN looks like. And then we said that RNN can be depicted in the following way, as we've seen over here. And it's sort of a continuous chain. And then we said that, so this is basically the latest form of RNNs that you should be familiar with. So now let's start talking about how can we actually have long-term memory if we keep RNNs in mind, or if we keep any deep neural network in mind. The question is that if you want to have long-term memory, suppose you're writing a C code or a Java code, right? And you want to, the same example that I spoke about, where you're talking about, you went to France and you want to, after a while, you want to keep track of where you are, all right? Or the other example that I gave last time was that, a particular person is narrating a story, and the person is, let's say, a male, and he's referring to himself, or you're referring to him as a he, and then the gender changes, and you have another person who's now involved in the story, and now it's a she. So you need to remember that the gender is either male or female, right? So suppose that you wanted to keep track of these variables when you're programming. How do you keep track of these? It's kind of obvious, but let's state the obvious. How do you do that? You have variables, right? So you may have a variable which says that, which country you're in, right? and you keep track of that. You say, I'm in France. Okay. And sometime later, when you need to use that variable, you refer to it and say, okay, which country was I in? So I'm in France. So so the language must be being referred to as French. Okay. So now imagine the complexity of that. Um, we now no longer programming as such, right? What's the basic difference between neural networks and the traditional algorithms? All of the computer science that you've learned so far and deep neural networks, what's the fundamental difference in the paradigm? Yes, so it generates the code. Essentially, the neural network is the code. Okay, so you're not really doing any explicit programming. All you're doing is creating the architecture, and somehow the weights as backpropagation is going on and so on, it eventually learns the function. Okay, so it's sort of a universal function approximator. All right, you have a certain input and you have a certain output, and somehow you want to be able to have some kind of a universal function approximator which can understand that. Okay, so that's basically what a deep neural network is. And it's different from a linear network in that it can be a very complex function that's learning, right? It could be all kind of complex, it has all kind of complexity, but somehow able to learn all of that. We saw that it was able to learn a spiral shape, okay? It could learn any kind of shape. It can learn a human face, all right? So you can imagine the complexity of that is completely non-linear, but it has the ability to be able to learn an arbitrary function, okay? X going to Y using a function. So in other words, you have Y is equal to f of X. Now f, this function, this is the input, and this is a function which is extremely complex. But somehow the deep neural network is able to learn that function, okay? And of course, these could be in a multiple dimensions. So this could be a 100-dimensional vector X and outputting a 50-dimensional vector Y, or maybe just a 1-dimensional vector Y, all right? But basically, that's the idea. So what you can't do anymore is that you can't define your own variables. Okay, you can't define a variable which says which country am I in, what's the gender, because there could be millions of such, and you can't predetermine what the variables are because you're not really doing the coding. The deep neural network is doing the coding. So then the question is, how do we keep track of these? How do we introduce variables, and how do we keep track of these variables in the long term? Okay. If you look at the RNN architecture, so this is the RNN architecture. Is there any continuity in terms of the variables that it is learning? So let's say, where would the variables be? So this would be WR, right? These would be the weights. So this is the variable that you're learning over time. It probably has a BR as well in it. And there could be a WI over here. This is the variable again that it's learning. WY is the output variable. This WR is not. So all of these are being learned. But can you see any continuity in that? As you're going forward, are these variables directly being passed forward? You can't really see that in this, okay? So this is one of the ways in which LSTM is going to try to do that, is by trying to have a continuity, okay? So it's going to somehow say that, and this is just a heads up, it's going to somehow say that I'm going to be able to have some kind of a conveyor belt that is going to keep track of some of the weights, some of the states, which you might call the variables, right? So the country and the gender that you would write in your traditional language, those need to be carried on, okay? So the way it's going to do it is by having some kind of a continuity, okay? So let's try to see how it's going to do that. It's going to do it by defining what is referred to as a cell state, okay? And as I said, this is sort of the variables which it's going to try to learn on its own. Again, these could be the two examples I used. This could be the country where you're in, the state where the gender of the person, or it could be a million other variables, okay? But as you can see now that I've drawn a direct line which is going, this is once, this is at time t, okay? And then of course, this is going to feed into the next, which is going to be at xt plus 1, okay? So as the inputs keep coming in, this particular cell is going to continue to change, okay? So basically what we're trying to do is keep track of the variables using the cell state, okay? And again, this is going to be, could be a very large dimensional vector, okay? And so it's going to clearly depend on the previous cell directly. It's going to directly feed it in. Now, we're going to try to do several things with it. We need to, for example, if you go from one country to another country, now all of a sudden, instead of being in France, you've gone to Germany, okay? Or as I said, the narrator of a story has changed. Now it's instead of male, it's a female, right? So what do you need to do about that variable? You need to change that variable, right? But in order to change that, what do you first do? You delete that, okay? So you have to forget that, and you have to add something new, okay? So the first thing that we're going to learn is that it somehow is able to, it has different stages. As it's going from CT minus 1 to CT, is going to go through different stages. What should be the natural stages that it should go through? What do you need to do to update a cell? What do you need to do? As I said over here, an example is a forget stage. So you need to forget about some of the things that are no longer relevant. You've gone to another country, forget about France, now you're in Germany. So you're going to first of all have a forget state, and then what are you going to have? You have an add state, an addition state, which is going to say, okay, which is the new country that you're going to give. So you're going to have what is referred to as an input state, okay, an input, and these are referred to as gates, okay. They're not referred to as variables, but they're referred to as gates. So let's first talk about what a forget state. So let's just refer to this later, but let's look at the forget gate. If you have a forget gate, it's going to be based on various data, okay? So obviously it's going to be based on the new input. So you have new input coming in, x of t. It should be based on that. It should be based on the past cell state, okay? Now we also have, in the past, we've also got an H, which is what? What does H stand for over here? The output of? What's the difference between H and Y and X? H was the hidden layer, Y was the output, X was the input, right? So it also had an H. Now, the classic LSTM, and we're going to look at various versions of this. This is the most popular version of this, but this is not the only version, okay? There are hundreds of different versions of LSTM which have been, have been proposed and researched, and you can come up with a different version as well, okay? GRU, which I talked about, is another version, okay? LSTM, the classic version of this, does use both the cell state, and it also uses the hidden state directly, okay? It doesn't necessarily have to. You could say, why does it need to use both, okay? The GRU, as you'll see later on, combines both of these and uses only one of them, and thinks that it doesn't need to have both of these, okay? It's a simpler version, it's a little bit more powerful. But let's look at the one which is well established and has been studied a lot. Now it uses the previous hidden state, it uses the input state, it uses the previous cell state, okay? Now what you want to do is you want to forget things, okay? Now, if you want to forget certain things, you're going to combine these, okay? And we're going to call this data that's coming in this vector, we're going to call it f of t, which stands for the forget variables, okay? The forget variables need to be either multiplied or added, or maybe some function that has to be subtracted or divided or something like that with the previous cell data and with the information that's coming over here, okay? Now, if it needs to forget, you think it should be a multiplication Or should it be an addition over here or some other version? How should be combined with the previous cell state? Now, remember when you're doing an addition, so let's say the previous value was a 1, you did an addition, and let's assume that you're doing an addition between 0 and 1, or -1 and +1, what have you, which would be the easiest way to forget something? You could do a -1, right? But then you would have to know what is the value of this, right? Suppose this was +2, then you'd have to do a -2. Multiply, and if you want to forget it, what would you multiply it with? With a 0. So the most logical way to forget something is to multiply it with a 0, okay? So if you're trying to forget something, then plus is not a very useful way, because then you don't really know. You need to find the exact opposite of that and then do it. And minus and divisions are basically other versions of the same thing, okay? So you're going to forget all about all of these. You're going to use a multiplication over here. So this is going to be a multiplication. Now multiplication, normally when you have vectors, you use a dot multiplication, what is also called a dot product or a Hamadad product or whatever. But it basically means these two have to be of the same size. So let's say this is A1, A2, A3, and you're multiplying it with F1, F2, and F3. Then it's basically output is going to be A1, F1, comma, A2, F2, comma, A3, F3, okay? So this is what, it's going to be a new vector, and it's simply going to be a dot product, okay? So these two have to be of the same, more or less of the same size vectors. Okay, so far we figured out that it should be a multiplication over here. Now, how do we calculate, how do we determine what the forget vector should be, okay? It's a combination of X and H. You could combine it with a particular, you obviously need to, if you're doing a deep neural network, what are the typical ways of combining things? You could add these two, you could multiply these two. Then of course you need to have the weights. Okay, the weights are where you're going to do the learning. And then you're going to have some kind of a activation. So we're going to display the activation over here. Okay, so here's some kind of an activation function over here. Now the question is, what kind of an activation function should it be? We've learned of several. We've learned of a sigmoid. We've learned of a ReLU. We've learned of a tan H. Okay, so tan H goes from -1 to +1. This goes from 0 to 1, and ReLU goes from, something like this. So now if you're trying to combine these two, and we've got some weights over here, so maybe we've got weights over here, we've got some weights over here. With each one of these weights, we will have some kind of a constant, bias as well, and those will all be combined over here, okay? So if you're trying to create a forget value, which one would be the most logical activation function? Should it be a value between -1 and +1? It should, I think that should be between 0 and 1. But a ReLU is between 0 and infinity, essentially. It can go up as high as possible. It doesn't clamp the values, right? So which one do you think is the best? Sigmoid seems to be the best. Why? Why would sigmoid, if you're trying to create a forget gate, why would you want to have a sigmoid? It's limited, so it's good idea to keep things within limits, because as you're going forward, if you don't have this clamping, then the numbers are going to become very big. So ReLU is probably not a good idea, but either a tan H, a hyperbolic tan, or a sigmoid would be okay. But if you're trying to create forget, which basically said that we're trying to zero out a lot of values, right? So this is 0 only at a very instantaneous value. Okay, so it's not probably very good if you want to zero out variables. This is better in terms of zeroing out, because as this becomes, as x becomes very small, it goes negative, then you basically, it goes between 0 and 1. Okay, so it seems a little bit more logical. But again, this is an open area. You could come up with your own, nonlinear activation function as well. But what LSTM does is it uses a sigmoid function. Okay, so the way it does is it combines these two. Okay, and here's the output. So the question now is, what should be the equation for the output? Okay, what should be the equation of the output? Can somebody tell me the equation of f of t? It's using sigmoid. So remember the previous equation that we used? No, don't tell me all that. Just use sigmoid, sigma, right? Sigma, and then sigma is going to be applied to something, right? It's going to be applied on what? Yeah, again, we're going to use the vector notation. So we're not going to do the summation, just simple notation. Remember the previous equations we have. So here's the example, right? We did the activation function and open brackets, and then we had some weights, the inputs. Okay, so here it was a combination of x and h, and then we had the bias. Okay, so now that I've given you a hint, can somebody now tell me again what would be the equation over here? Sorry, weight into xt. So it will be some weight into x of t, right? Plus some other weights into h of t minus 1 plus a bias, right? Okay, so this is fine. A shorthand notation of this is that we could use different weights over here. So sometimes people have said w and u over here. You'll find this as well. You could say, because this is a forget state, so we could use an f over here, right? So all of the biases, all of the weights are now have a subscript of f because it's a forget state. Okay, or what you could also do is you could combine both of these, and you could say this is basically wf, and we write it this way, into x of t plus h of t minus 1. Okay, so these two notations are the same. The only thing is what I've done is now I've combined these. So wf will now be, will it be the same? So let's say if I call this wf prime, will wf prime and wf be the same? Will they be of the same size? Will the vectors be the same size? Will the number of weights be the same? Now we're combining two different variables, right? So it's essentially like saying that we have, this could be h of t minus 1, and this is x of t, okay? And now we're combining both of these. There are two ways of combining these. One way is that we combine these separately, okay? So this was w prime, and we did this combination, and u. Or what we could do is we could combine both of these together using a single weight, okay? So if we're combining both of these together, will these two, will wf over here have the same structure with the same vector size? It should be the same size as what? As x of t or h of t, or a combination of them? Combination, right? So now this wf, when I'm writing it like this is actually has a, it's going to have, if w prime was of size, let's say 100, and this was of size, let's say 200, then wf is going to be of size 300, right? Because now it has combined both of those two, and I'm now writing it in a simpler form. We basically, what we're doing is we're writing it in a simpler notation. Instead of introducing two variables over here and replacing it with a single variable, that's all it is. You could write it in both ways. Okay. So, so this is the result. Um, so you can see that we've basically replaced this with the following, and this is how we're going to show it. If you notice this, this is sort of like combining these two, okay? When it's shown like this way, and both of these are inputs, sort of like merging in, okay? So this is a notation which I had earlier used as well. If you remember some time back, this is notation that I'm now using, it's concatenation, okay? And this is like copying, okay? And this is the, these are some notations that we're going to be using. So what we've done is basically merged these two, concatenated them, okay? And we've added a B of F over here. So this is the point where I'm showing the weight WF, okay? I'm not showing it over here. I'm not showing it over here. I'm showing it where the two have already been merged, okay? And there I'm also showing the bias, okay? So this is the notation that I'm going to be using. So we've understood that this is the forget gate. It's basically doing a combination of these two, and okay. So so far so good. We've got the forget gate. Now the question is, how do we construct the input gate? Do we want to now add some more input? So could we use the same example and try to construct an input gate? Are people online, still online, and they can hear me?
Yes, sir.
Yes, sir.
Okay, good. So how do we construct the input gate? Can we do the same thing? Okay, but we somehow need to combine the input gate. So let's say this is a combination over here. We're trying to add the input over here. So first of all, what should we have over here? Now we're trying to, with C of t, we're trying to add something. Earlier, what we had done is we had used a multiplication. When we're now trying to add something, should we use a multiplication or addition or something else? Should we use addition? Does it seem logical? Because now we're trying to add something. We're not trying to forget something. We're trying to add something. So what we're going to use is we're going to add it on. Okay. Now, the question is, what should we add in over here? So what we could do is perhaps have some kind of a data I of t. Okay. What should we have over here as the activation function? Now we're trying to add something. Maybe should it have to be between 0 and 1, or it could be anything, right? So we could do ReLU. ReLU doesn't have negative values, by the way, unless we're talking about leaky ReLU, which I haven't talked about, which has slightly negative values. But what has negative values as well? Tan H, right? So what we could do is use tan H, right? So I'm going to show it as a T over here, okay? But tan, if you remember, we already know what tan is, right? So it's some function, which is between -1 and +1. So the natural way of adding something, it would be nice if we had a tan function. And what we could do is just like we did before. I'm going to try to erase these two, but I think I can't. Anyway, so I'm going to now. Okay, so this is where I'm doing it. So I'm adding a plus over here. I'm going to add something. So I'm going to use a tan over here. And I'm going to, again, use the previous values of H and X. And I'm going to connect them over here. Okay, so does that make sense? We're simply trying to replicate what we did earlier. Of course, the weights are going to be different over here. What should we call these weights? So let's say if we're trying to add something over here, this could be I. So we could have WI and BI. That stands for input. Okay. And let's say we're trying to add something over here and we're creating a tan. Okay. Now, the tan will create values between -1 and +1. Okay. So now this is going to generate a bunch of values. Okay. So this is one way that we could do it. Okay. Now, the way it's actually done in LSTM is that instead of simply doing it this way, they also have another mechanism by which they're trying to control this. So they want to be able to say which of these values is generated a whole bunch of, so it has, let's say, 300, the vector of 300, okay? Now, you want to be able to add some of those, not all of them. So how do we select from this? How do we want to select some of these? In other words, some of these we want to keep, some of these we want to discard, right? Sort of forget. So, sorry, on what basis again? We don't decide that. All we do is create an architecture which has the ability to learn, okay? So again, it's going to be all based on backpropagation. We're going to apply the same techniques. We're going to apply gradient descent. And that is hopefully going to be able to train the weights over here, and weights over here is going to be able to say, okay, this is what I need to forget. This is what I need to retain. Okay, this is what I need to add. Okay, so we're not going to ask the question, how do we know? That backpropagation and gradient descent are going to be responsible for that. Okay. All you need to do is give enough training data, enough label data so that it can actually learn. Okay. So the question is, how do we forget some of these? How would we do that? So think about what we did over here. What did we do over here? If you wanted to forget some of the past cell states, what did we do? We multiplied it by something. We multiplied it by a sigmoid, right? So can we do that over here? We want to be able to forget some of these. So how would we do that? So before this goes out over here, okay, before this goes out, what should we do? We could use sigmoid again to forget some things, and then how should we combine it with this? Should we use multiplication or addition? Multiplication, right? So we're going to do a multiplication over here. So we're going to take a sigmoid, and again, it's going to take input from past h and x of t, okay? And in fact, this is what they call as input, okay? So this WIBI is used over here for the weights. And this is referred to as, I guess they couldn't come up with something better. They refer to it as C tilde. This is the, just refer to it as C tilde for now, instead of confusing you with the name. So we're going to use this input over here as C tilde. Is going to be combined with I of t, okay? And the I of t is basically going to decide which values of the addition do we forget, okay? And what are the additional values that we want to add? We're going to use a tan over there. So we're going to generate a whole bunch of values between -1 and +1. Then we're going to multiply it with a sigma generated I of t. We're going to multiply that over here. That will ensure that some of these will be used, some of these will not be used, okay? And so now can you write an equation for C of t? So based on f of t and t tilde and I of t. So is it so? Okay, so he's saying, okay, let's do it partially. इसको अगर मैं Z कह दूं, okay? Can you write an equation for Z? C tilde t multiplied by I of t. Okay, now sometimes people use notation like this to indicate that this is a dot product, okay? But I'm just going to say multiplication, keep it simple. So this is going to be C tilde t, and this is multiplied by I of t, okay? So if you look at CT, what should it be? Sorry? So if I write this over here as, let's say, Zx, no, let's use alpha over here. So what would be the equation for alpha? F of t multiplied by Ct minus 1, okay? And then C of t would be what? Is there a tan H now? All I'm doing is taking alpha, and what am I doing with Z? These two. I'm just adding these two. So it's very simple. All I'm doing is saying that it's simply alpha plus Z. Is that making sense? Right, so all it's doing is this is the equation for C of t. And what is alpha? We've got it over here. What is Z? We've got it over here. Okay, I'm just introducing these variables to make it simple. What is Z now? Oh, we've already done that. Okay, so what is Ct tilde? So it's going to be T of, and let's introduce some weights over here. So I'm going to call this WC and BC. So what is it going to be? WC x of t plus, sorry. So sorry, I'm not, did I write a plus earlier? No, I didn't. So it's going to be a comma over here. Okay, because we're not, as you can see, comma is different from a plus. Okay, a plus was vector-wise summation of corresponding terms, but this is basically a concatenation of those two. So 100 plus 200 becomes 300. Okay, so x of t, h of t minus 1. We're going to show that by using these square brackets. What else? Plus the bias, which is b of c. So you've got the equation for C t tilde. What about I of t? What's the equation for I of t? Sigmoid of, sorry, wi x of t comma h of t minus 1 plus b of I. Okay, so we've essentially solved everything so far. Okay, have we solved for C of t? So far, based on the forget gate, which we've already done earlier, and based on the input gate, this is the entire input gate, we've now been able to create what CT is there. Now, you would think that this seems enough, but we have something hanging over here. We haven't figured out what is the new value of the h of t, and we haven't really figured out what is the output y of t. Okay, so we still have a gate left, which we are going to call as the output gate. Okay, so this is just the equation that I've rewritten over here. Okay, this is the same thing that we just saw. Now let's try to figure out what the output gate should be. G. Sigma is used, yes. So sigma is a value between 0 and 1, and is used for two purposes. One is to clamp the value to 1 so that the variables don't go up to infinity. And the other is when you want the output values to be between 0 and 1. Okay. If you don't mind having between -1 and +1, you can use a tan H, but otherwise you'd use a sigmoid. Okay. Producing values, yeah, that's a good way to think about it. Okay. in forgetting, right? Yeah. In which gate are we talking about? In, so let's say we're looking at the forget gate. Your question is that how is the sigmoid helping us in forget? Okay, because देखें यहाँ पर क्या हो रहा है, you're learning weights, right? You're learning what weights are you learning? You're learning the WF and BF, right? Now, if these are learned properly, then it's going to, so suppose that one of these weights corresponds to a feature which was a country. So if that weight becomes, if that is multiplied by a 0, in other words, if you are, let's say, you have a vector. Okay, so let's say these are the two vectors, vector space, right? So this particular value corresponds to, let's say, the country. Okay, and now you have an activation function which is going to take these weights and multiply them by by something between a 0 and a 1. Okay, so if your weight over here between the weight and the sigmoid function, if you can figure out that you have to actually make the result 0, then that particular feature will be forgotten. Okay, so this is a little tricky as well, but think about it some more. Maybe as you go through this, we'll develop a better understanding. But basically, what it's doing is developing these weights and the biases, and those are controlling what you have to forget. Okay, so these weights are going to determine, these weights and biases are going to determine what to forget and what not to forget, which features to forget and which features not to forget. Okay. Okay, so we've gone through the forget gate, the input gate, and now let's talk about the output gate. Okay, now the output gate is not so obvious what we have to do. All right, and I'll just tell you what the way it's done, and let's try to see if we can figure out what's going on. Okay, what it does is it takes a tan over here from the CT. Okay, and it I think it does. No, it does the multiplication. Okay, so it does a multiplication over here. Okay, it uses a sigmoid function over here, and it combines it. Okay, so over here you're going to have certain weights. So over here we had certain weights, we had weights over here. So this is going to be a separate branch in a sense, which is going to have certain weights. We're going to call these WO and IO, because now this is going to produce the output. Sorry, the not the input, but the output. Okay, O of t. Right. So if we try to write the equation for h of t, how would you write it? Sorry. So let's write O of t first. So what would O of t be? Sigmoid of WO x of t comma h of t minus 1 plus b of O, right? Remember, we're using different weights in every stage. So we've got new weights over here. That's O of t. Now what is h of t now? O of t multiplied by tan h of c of t. Okay. So this is what the output is. You might try to figure out why this is used, but again, this is an architecture which somebody's come up with. They probably had some good insight, which I'm not sure why they used this particular combination. But basically, this is giving the a set of weights which can be used to control the h of t, okay, the hidden variables. And it's also taking input from c of t, okay. And the output over here is actually just y of t. Y of t is equal to h of t, okay. So this is the standard LSTM architecture, okay. Y of t is simply the hidden output, okay. And the hidden output is a combination of C of t and O of t. The output O of t is basically has weights which are being used to control the value of the hidden variables, okay. G. So, sorry, फिर से कहीं h of t minus 1 and x of t concatenate हो रहे हैं, बिल्कुल सही है. That's a very good question. I've never thought about that. Let me just think about it. So let's see, the output is now combination of x and h. You're absolutely right. So if we look at this particular question, आपका नाम क्या है? Zishan, that Zishan has asked, will h of t continue to become bigger and bigger? So let's think about it. Ji. देखिए sigmoid तो यहाँ पर already है. The point is that O of t is actually has both of these concatenated in it, right? So O of t is bigger than both of either one of these, right? If O of t is bigger than either one of these, and we're taking a multiplication of this, so the question is, huh? So it seems like what you're saying, Zishan, is true, is that it is becoming bigger. Does anybody have a comment on that? Okay, sigma is only clamping. That's not what Zishan is saying. He's saying that if this was a variable which had 100 vector, it was a variable with 100 variables, and this was, let's say, 200. Okay, let's say this is both 100. Okay, so this now becomes, the output now becomes 200. Okay, this is now 200. So, sorry? X of t, so let's say okay, this is also, this is, let's say, 50. Okay, so this is now 150 over here. Of t is now 150, right? And this is now, these two are already of size 150, right? And you're adding 150 to 100. That's a good question. So, I mean, you've raised an interesting set of questions, and honestly, I haven't looked at this aspect. Okay, let's look at this in more detail. Hopefully I'll try to come back to you. I don't want to get you confused right now unless I've taken a look at it, but this is a very important and interesting question. So, so this is basically what we have over here. Overall, we figured out what the LSTM is doing. We haven't figured out what the issue of whether the size of the vectors is expanding or not. And if it is expanding, there is a problem. Maybe if it's not, maybe there's something going on that we're not aware of. The best thing is to actually read the LSTM paper, and maybe that addresses it. Okay, G. C is sort of the cell state. Remember when we started talking about, so if you look at this, basically, if you look at RNN, when we started off, we said that there's nothing continuing. Okay, यहाँ पर you can see that C of t minus 1 C of t is continuing. Okay, it's being multiplied by certain things that you want to forget about C of t. It's adding certain things that you want to add to C of t. Okay, so it's quite possible, if I just thinking about it, that maybe it does need to expand because there could be new variables that you need to add. All right, so it's quite possible that C of t and C of t minus 1 are not the same. Maybe the size might reduce, maybe it might increase. We'll think about it. But conceptually, it is possible that even as you're writing your program in Java, as you're going forward, you're having new things, new information coming in, you need to keep adding that. So your vector size might start off with very few features, but at the end of it, you might have a lot more features. Okay, so maybe that's what's happening. But you can see that this is sort of like a conveyor belt. Okay, so this is a conveyor belt which, as you're going forward, there is a cell state which is continuing. Okay, and it's being added, modified, and so on. But this is the cell state which is continuing throughout. Okay, and things are being added to it as new information comes in, things are being added, and so on. Okay, so this is basically as far as LSTM is concerned. Now there's something called a GRU. So this is an alternate to LSTM. So it sort of indicates that this is not the only solution. Okay, here's an alternative which is actually simpler. Okay, and it combines some of these. So it combines some of the gates together, forget and input gates into a single update gate, and it merges the cell and the hidden state. So as I said earlier, it doesn't have a separate cell state. This is the H of t is sort of now a combination of the cell and the hidden state, and it's combined together to go forward. Okay. Let's try to see if we can write an equation. Okay, so let's first of all see how would we write an equation for some of these. So let's see how we could write an equation for the GRU. Okay. Okay, so we've got variables over here z, we've got r, we've got h hat. Okay, so where do we want to start off with? Let's start off with h hat of t. So can somebody tell me, this is a different notation, but simply you can forget this, but I'm just showing you different notation that people have used. Okay, so what would be the equation for h hat of t? Okay, good question. So 1 minus basically what this does, this is a new kind of an operator. What this is doing is the output over here, will be 1 minus z of t. Okay, that's what it indicates. So let's see if we can write the equation for h hat of t. So tan multiplied by, so what are we going to have over here? We'll have some kind of weights. So let's call these W, H, all right? W, H, B, H. So it would be W, H, and it would be a combination of X of T. And then, so you can see that this is a combination of X of T and what is happening over here. It's combining with something else. So I'm going to call this, let's say, for lack of a better term, let's call this beta. Okay. So what is it doing? It's combining X with beta, right? And I'm going to add another term over here, which is going to be the bias. Are people with me so far? Okay. Beta is going to be what? R of t into h of t minus 1. So this is combining this with h of t minus 1. Okay, so we've got So, sorry, where? Because of the RT, we're simply taking RT right now. So we haven't calculated what RT is. So what's RT equal to? Sigmoid of, so this is now a combination of, we're going to add some values. So let's call these the weights over here, or rather the weights over here, W, R, and BR. Okay, so WR times X of t combined with H of t minus 1 plus B of R. Okay, R of t ho gaya. What else is left? Okay, so let's calculate Z of t. What would Z or Z, as you prefer to call it, be? Sigmoid of, and we could have the weights WZ and BZ over here. Okay, so WZ applied on X of t and H of t minus 1 plus B of Z. Okay, so you've got Z as well. Now what do we need to do? We need to calculate H of t. Okay, let's calculate this over here. I'm going to call it theta. So what would theta be? H of t minus 1 multiplied by 1 minus Z of t, right? Okay, and let's call this gamma. What would, right over here, what would gamma be? It would be H tilde of t into Z of t, right? So Z of t, H tilde of t, that becomes gamma. And what is finally H of t? H of t would be theta plus gamma. Okay, so this is quite different from what we've done before, right? One of the unique things about this is that it has a 1 minus Z in it. Okay, it's sort of taking the inverse because Z is between 0 and 1. So it's basically taking the opposite of it, right? So if it was 0.9, it would be 0.1, and if it was 0.2, it would be 0.8. Okay. What else is it doing which is different? Sorry, कौन सा symbol? Concatenation symbol. I don't know. This was, I found this somewhere, and it's simply some notation that they're using. No, there's nothing there. You can just forget about this. Okay. So I'll have to look into that. I mean, you could have a point. I'll look into this because it wasn't used typically in every place. In one of the places where I got this from, this particular image from, it was used. So we can look into it. Okay, what is that? What particular? But as far as my presentation is concerned, I'm sort of right now ignoring this. Okay, it may have a finer meaning. So we've got an idea what the GRU is. So this is what the simplified equations would be. You know, if you can double check that, hopefully there are no mistakes in that. Okay. So, so this basically ends our topic on LSTM and GRUs. As you can see now that if you apply this technique, then basically how have we gone beyond the RNNs? If you think back at what was the original problem in RNNs, um, we wanted to have long-term memory, all right? So is this somehow retaining the variables over the long term? Do you seem to be convinced about that? Hmm. Hmm. So if you think about this chain that we showed over here, so let's say there was something over here and there could be a big gap over here. So let's say okay, there were 100 other cells in between, okay? And this is again in time. Remember, this is all in time. This is not saying that each one of these weights is separate. These are not separate weights, okay? So if I write a weight over here, and if I say that the weights over here are WF, are these WFs all different weights, or are they all the same? They're all the same. So it's simply the WF changing over time, okay? And as we saw in the RNN, it's going to use backpropagation to be able to train all the data. So it's going to use all of this data all together or in sequence to be able to train it, okay? So it's backpropagation and time which is going to be used, okay? So now let's think about this. If you've got a big gap over here, all right, so you started off with the problem that you went to France and way later, so you have a statement, you saying over here, I went to France, blah, blah, blah. And then after much later, you're trying to figure out what this term over here should be. Okay, which language are we talking about? So somehow this and this over here, when we spoke about France, let's say over here, these two need to be connected together, and they have to be somehow the vanishing gradient problem has to be resolved. Okay, so the issue is by having these cell states over here continue on, somehow the vanishing gradient problem has been addressed. Okay, that's what the claim is. Okay, we'll have to think a little bit more about it as to why, and you might have to read the paper as to figure out why can you convince yourself that the vanishing gradient problem has been resolved over here. Okay, but even LSTMs are not perfect. So what's been seen is that LSTMs were quite a rage for a while. Okay, I think for many years, they were the best solutions, and GRUs, some small modification of this. Recently, I think over the past 3 to 4 years, there are other techniques which have come in, okay? And these are based on a technique called transformer, okay? That's a little bit more complex, and it's far more complex, so I'm going to actually try to talk about that much later, okay? So we talk about transformer, which are basically a much more complex version of LSTMs and GRUs, but we'll reserve that maybe to a few weeks later, okay? But basically the idea was that by having a cell state and forget states and input gates, you've somehow been able to overcome the issue of the vanishing gradient problem. Okay, that's the argument.